In this video, I'm going to be looking at the partial pressure, density, and diffusion behavior of gases. To begin, let's review the kinetic molecular theory of gases. Remember that this is 5 postulates about how gases behave. Taken together, they tell us that we can pretend that all gases behave the same way, or adhere to the same set of equations. This is why things like Boyle's law, Avogadro's law, or the ideal gas law work for all the equations we've dealt with so far. One new equation that we can look at is Dalton's law of partial pressure. Dalton's law of partial pressure states that each gas exerts a separate pressure on the container it's in. Therefore, the total pressure exerted on a container is the sum of the partial pressures of each individual gas. Now, if you've been watching my videos, you know that this is Dalton's second appearance in this course. He was wrong about his model of the atom, but he's right about this. It's nice that he gets a chance to redeem himself. Visually, what Dalton's law of partial pressure looks like can be shown right here, where you might have a container full of hydrogen gas under a pressure of 2.9 atmospheres. Next to that, you have another container full of helium gas under a pressure of 7.2 atmospheres. If you were to combine the hydrogen gas from the first with the helium gas for the second, the total pressure can be calculated by summing the two individual pressures. Likewise, if we look at our atmosphere is composed primarily of nitrogen and oxygen, also with trace amounts of argon, water vapor, and carbon dioxide. Summing the partial pressures, or the individual pressures of each of those gases, you get the total pressure of air in our atmosphere of 101.3 kilopascals. Mathematically, what we're doing in both of these cases can be summarized with this equation, which is our equation for Dalton's law of partial pressure, where the total pressure of a gas is equal to the pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3, etc. Let's now look at a sample problem that involves Dalton's law of partial pressure. The question states that a 3-liter container holds 4 moles of oxygen and 1.7 moles of helium at 285 Kelvin. What is the partial pressure of oxygen? What is the partial pressure of helium? And therefore, what's the total pressure? A reminder here that Dalton's law of partial pressure tells us the pressure of the oxygen plus the pressure of the helium is going to equal the total pressure. It's that simple. So we're going to set up two separate equations here. The partial pressure of O2 can be calculated using the ideal gas law. And the partial pressure of helium can also be calculated using the ideal gas law. The only value that's going to be different in these two equations are the number of moles, and of course the pressures that we're calculating for these two. Once you have those two pressure values, you can sum them and get the total pressure. When I set these equations up, my math gives me a pressure of oxygen equal to 31.18 atmospheres and a pressure of helium equal to 13.25 atmospheres. Again, I was using the ideal gas law and rearranging to solve for pressure. My temperature is already in Kelvin, so I didn't need to convert there. And lastly, to solve for the total pressure, I will sum those two partial pressures and get a total pressure of 44.43 atmospheres. That is a lot of pressure. Next, let's look at one more instance where we can pretend that all gases behave the same way, and that's going to be with the density of gases. The density of gas is typically given where density equals B, or grams over liters. This definition of density and the ideal gas law, we want to use those two to derive an equation that only has density on the left side and has our other variables, pressure, temperature, molecular weight, on the right-hand side. To start, let's think about molecular weight. Molecular weight, or molar mass, is equal to grams over moles. So let's rearrange that second part of this equation a little bit and solve for moles. Moles would then be equal to grams over molar mass, or using the vernacular here, moles equal grams over molecular weight. Now let's look at the ideal gas law, PV equals nRT. There's moles, and there's moles. So to help us with this derivation, let's plug grams over molecular weight in for moles. That gives us PV equals grams over molecular weight times R times T. Now, eventually I'm going to want density alone on one side of the equation, which can be described as grams over liters, which are also both in this ideal gas equation. So I'm going to work to try to get grams and liters by themselves. The way to do that will be multiplying through by molecular weight and dividing by RT, and then dividing by volume, grams over volume. Simplifying that equation a little bit, I want to give myself some more space. Simplifying that equation a little bit, get density, grams over volume, is equal to P mW over RT. That's this half right here. A reminder that density equals the pressure of a gas times the molecular weight times the gas constant times the temperature. Here's an equation that'll work for all ideal gases, but we see our first glimpse of gases that are going to behave a little bit differently, because gases at different molecular weights will have different densities. Let's use this equation in a practice problem. I want to calculate the density of ammonia at 850 torr and 100 degrees Celsius. So there's a few things we'll need to do. First, we'll need to find the molecular weight, or the molar mass of ammonia. Then we'll need to convert torr to atmospheres, and finally we'll need to convert degrees Celsius to Kelvin. Those values are equal to 17.04 grams per mole, 1.12 atmospheres, and 373 Kelvin. Now we can use our density equation. Density equals pressure times molecular weight over the gas constant divided by the temperature, and solve for the density of this ammonia gas. Our pressure is 1.12 atm. Our molecular weight is 17.04 grams per mole. The gas constant, 0.08206 atmosphere liters over moles Kelvin. And the temperature in this case, 373 Kelvin. A quick check on units. Atmospheres cancel, moles cancel, Kelvin cancel, and I'm left with the units of grams per liter, which sound like a good unit of density. Calculating this out, I get a value of 0.624 grams per liter. Let's look at one additional problem. If air is 78% nitrogen and 22% oxygen, we'll ignore trace gases for a moment. What's the density of dry air on a cold spring day at sea level? Again, we're going to ignore water vapor. So the pressure is 1 atmosphere, the temperature is 5 Celsius. You've got a mixture of gases here. It's a good challenge problem. See what you come up with for that. The answer will be at the end of the video. One final equation in this video is going to deal with movement of gases. And first, two quick definitions. Diffusion is the spreading out of a gas from a concentrated source. This is due to the random movement of particles. So here we've got a red gas diffusing out into this yellow gas. Diffusion increases entropy, and one of our rules in chemistry class is that the universe likes an increase in entropy, so gases will definitely diffuse. Also, remember that gas particles themselves are moving very, very fast, maybe hundreds of meters per second, but rates of diffusion are relatively slow. You can envision this from everyday experiences, such as smells taking a little while to waft through rooms. That's because the movement of gases on the aggregate is much slower than the individual particles moving. We can contrast diffusion with effusion, which is the movement of a gas through a small opening. That is a very specific case of diffusion. You see a good example of that there, where you have the gas effusing through this small valve. Another really good example of this might be a puncture in a bike tire or a car tire that produces a slow leak where air is going to leak out of that tire. This is what I want to focus on an equation for. To do that, we're going to look at Graham's Law of Effusion. Graham's Law of Effusion is going to describe the relative rate of effusion between two gases. Note the key here is relative rate. So first, I want you to consider two gases that are at the same temperature and have the same kinetic energies. Kinetic energy can be described as kinetic energy equals 1/2 mv squared. So from that, we can say the kinetic energy of gas 1 equals the kinetic energy of gas 2, because again, they're at the same temperature. From that, we can replace the equation now and say that 1/2 mv squared for gas 1 is equal to 1/2 mv squared for gas 2. Again, same kinetic energies because they're at the same temperatures. Then we can simplify and get rid of that half and say mv squared for gas 1 equals mv squared for gas 2. Rearrange a little bit and get v1 squared over v2 squared equals m2 over m1. And then oftentimes you see this equation simplified a little bit where we square root both sides and get v1 over v2, or the velocity of gas 1 over the velocity of gas 2, equals the square root of the molar mass of gas 2 or the molar mass of gas 1. That gives us Graham's law of effusion. And we can simplify velocity into a rate of effusion. Rate of effusion of gas 1 over rate of effusion of gas 2. That ratio, that relative ratio of the rate, equals the square root of the molar mass of gas 2 over the molar mass of gas 1. So what does that look like? Well, let's look at two different practice problems. The first question reads, a certain gas effuses 4 times as fast as oxygen gas. What is the molar mass of that unknown gas? What we want to do here is identify our gases. Oxygen we can call gas 1, and our unknown is going to be gas 2. So Graham's law of effusion tells us rate 1 over rate 2 equals the square root of m2 over m1. Well, let's put in some values now. We can say that the rate of effusion of oxygen is equal to 1. There's no units because we're just talking about a relative rate. We know that our unknown gas is going to effuse 4 times faster. So that rate would be equal to 4. Equals the square root of a molar mass of our unknown gas, which we don't know, over the molar mass of oxygen gas, which we do know. To solve this, square both sides. Then cross multiply, get 32 equals 16x, and finally divide by 16 on both sides to get x being equal to 2. What gas has a molar mass of 2? Well, that's hydrogen gas. Another sample question here reads, if 0.00251 moles of ammonia effuse through a hole in 2.47 minutes, how much hydrochloric acid would effuse at the same time? Pause your video for a second, work through this problem, and the answer will be at the end of the video. If you have an answer, you can continue on. I'll leave you with a good thought exercise here. Suppose the following data was collected by an experimenter who was observing the distance traveled by various gases in a set amount of time through a horizontal glass tube at room temperature and pressure. There's our 4 gases, and there's the distances they traveled. I want you to state your observation as briefly and to the point as possible, design a hypothesis to explain your observation, and then suggest an experiment to test your hypothesis. Pause the video, think about this, and when you're ready, you can continue on and I'll reveal the answers for the 2 challenge problems throughout the way. Thanks so much for watching.